Okay, it's Brian again. We're going to continue our discussion of force and motion that we started in the last set of slides. And as a reminder, basically what we're doing is we're telling stories. We're going to look at emotion. We're going to tell two stories. One, a story about the motion, and our big interest is what is the acceleration. The second piece of the puzzle is the force story. And in that one, we want to know what is the net force. And the net force and the acceleration are related by Newton's second law. So we're going to have two parallel tracks. And we saw in the last set of slides, we drew motion diagrams to figure out the acceleration, and we do force diagrams to figure out the net force. Today, we're going to go ahead and take those diagrams, we're going to connect them to equations, and actually start doing some numbers. Now I want to remind you of what we talked about with friction and what you read about in chapter 4 about friction. Okay, so there's static friction where the surfaces are not sliding, kinetic friction where they are, and then rolling friction. Each one of those, the friction force depends upon the normal force and a coefficient of friction, and there are different values for different sorts of friction. There's a table in chapter 5 where you can look those up and see what those are. Those are numbers that we'll need to use in solving problems if the friction coefficient is not given to you. Now let's go ahead and take a look at the type of problem we're going to be solving. So this question asks this: what is the shortest possible time in which a car could accelerate to 27 meters per second if we're assuming a coefficient of static friction of 0.85, and that's static friction between the tires and the road surface. And I know the previous slide said it was more like 1, but this is under real-world conditions. And under real-world conditions, the coefficient of friction between a road surface and tires might be about 0.85. That's a reasonable value. And we'll see that ultimately what limits the acceleration of a car isn't the engine under the hood. It's where the rubber meets the road. Okay, and we'll talk about this. But we're going to do this the way we solve these kinds of problems. We're going to start with the motion story and the force story. So when we solve this problem, we're going to start by drawing a free body diagram and a motion diagram. Okay, that's going to be our starters. And then we're going to look at the x and the y components for the net force. And only then we're going to start using the equations to tell us things about the motion. Okay? We're going to start writing down a couple of equations. We're going to calculate some things, and then we're going to end up with calculating finally the minimum time to go from 0 to 60. But there's a bunch of steps to get there. Now our first piece of the problem is we're just going to strategize. That's how we start all of our problems. And the strategize step, we just want to chart a path through the whole problem. And what I'm going to do is this. I'm going to say I'm interested in time, okay, but I'm going to get time from knowing acceleration, and I'm going to get acceleration from knowing about forces. So basically what I'm going to do is this. I'm going to look at the forces. I'm going to use that to tell me something about acceleration. And acceleration I'm going to use to tell me about time. That is the basic process that I'm going to use to work my way through the problem. But next, let's get rid of our strategize information, and let's talk about how do we prepare. Okay? Next piece is preparation. Okay, so we're going to prepare. Now the preparation step is what's outlined over here. And the first piece of the puzzle is to draw a free body diagram and a motion diagram. And I'm going to start with the motion diagram. For the motion diagram, the car is accelerating. It is speeding up. And so I end up with a series of dots, which are getting further and further apart. That tells me I have an acceleration that is directed to the right. My free body diagram is going to look like this. We know there's a downward weight force acting on the car. There always is. There's going to be an upward normal force from the road surface. That's just the component of the surface force that is perpendicular to the road. And then I have to have a force to the right. There has to be a force to the right. And the only possible thing it can be is a force from the road on the car. And the only horizontal force from the road on the car is the friction force between the tires and the road surface. And so this is going to be the static friction force. Static friction force is typically greater than kinetic friction force. And if I want the shortest time, I want to have the biggest possible force, and so I want static friction. Okay, the next piece of the puzzle is to think about this. What is F net? the x and the y components. So I'm going to look at my free body diagram. And for my free body diagram, let's do the x component first. So F net, if I look at the x component, it's just equal to Fs. There's precisely one force in the x direction, and that's Fs. How about in the y direction? F net in the y direction is equal to the force that's pushing up minus the force that is pushing down. So I can write down those two relationships. What I've done is I've taken my free body diagram and I've turned it into two equations for my x and my y axis. Next, what I do is I talk about Newton's second law. And what does Newton's second law tell us for the vertical motion? And then we want to talk about what Newton's second law tells us for the horizontal motion. Okay, so let's go ahead and do that. Let's go ahead and do that. So first, we're going to look at the vertical motion, so for the y motion. And in the y direction, the acceleration is equal to 0, so F net is equal to 0. So that tells us n minus w is equal to 0, or n is equal to w. In the x direction, it's a little bit more straightforward. We just have the acceleration is equal to F net divided by m. And so the acceleration is just going to be equal to the static friction coefficient divided by m, because in the x direction, the x component of F net is just equal to Fs. Now these two equations, this one here, n is equal to w, and the acceleration is equal to Fs over m, are two things that we can take forward to the next phase of our problem solving, which is the actual solve step. So we're going to hang on to those two, but we're going to get rid of everything else because the next piece of the puzzle is solving. Okay, so let's get rid of all the other details and just hang on to those pieces. Actually, I'm just going to get rid of everything. That's going to be easier. And then we can go ahead and take a look. We can put those pieces in. Okay, so the next step is our solve step. Now for the solve step, let's remember those two equations we had. We had the acceleration was equal to Fs over m, but we also had that the normal force was equal to the weight force. And we can do some further simplifications because we know something about the weight force. The weight force is just equal to m times g. So we can rewrite this as the normal force is equal to m times g. We also know something about the static friction force. If I want the biggest possible acceleration, I want the biggest possible static friction force. And the maximum value that the static friction force can have is just equal to mu s times the normal force, and that's what we want. So the acceleration for the case we want is just equal to mu s times the normal force divided by m. Oh, but check it out. The normal force is equal to m times g, so I'm going to take that, I'm going to put it in here, and then I get the acceleration is equal to mu s times m times g divided by m, or it's just equal to mu s times g. It's equal to mu s times g. Okay, with that in hand, then I can go back and I can say, oh, I can compute a value for acceleration because I know a value for mu s and I know a value for g. And if I do that, I get a value for the acceleration of 8.3 meters per second squared. Okay, that's going to be my acceleration. With my acceleration in hand, I can calculate the actual thing that I want, which is the time. So thinking back to our strategize step, we started with forces, and then after forces, we worked our way to acceleration. Having got into acceleration, our next stage is to go to time. And from acceleration to time, that's back to the stuff that we learned in chapter 2. And we know the acceleration is equal to the change in velocity divided by the time interval. And so the time interval is just equal to the change in velocity divided by the acceleration, And if I put in numbers, the change in velocity I'm looking for is 0 to 27 meters per second. So the change is 27 meters per second positive, divided by the acceleration, which is 8.3 meters per second squared. And that gives me a time interval of 3.3 seconds. Okay? 3.3 seconds. Now the next piece of the puzzle, of course, is we want to assess. We want to look at that answer and see if that's reasonable. And the easiest way to do that is actually just to look at data. So I'm going to look at data, and I got this from Car and Driver, and I looked at like production vehicles, and I looked at their 0 to 60 time, and you can extract it from this graph. And the shortest 0 to 60 time I see on the graph is 3.6 seconds. So we said the shortest possible time was 3.3 seconds, and that is determined by the friction between the tires and the road surface. And so no car should be able to do better than that. In fact, no car was able to do better than 3.6 seconds. And so our assessment is that current cars are doing about as well as they can. This makes sense in terms of understanding about how the world works. Now, there are things that you can do to achieve a bigger acceleration. And let's take a look at one. And this is something we'll talk about later, but you can get a better acceleration if you have wings that push down. So check out the wings on this Formula One racer. The wings actually push the car into the road surface. It actually pushes the car into the road surface. And I want you to think about, why would this permit greater acceleration if I push the car into the road surface? And so basically I have a lift force, but it's pushing downward. That permits greater acceleration. Why is that true? I think I want you to go back, and I want you to take a look at the calculation that we did and all the details and see if you can make sense of that. And I want to mention, too, there are actually birds that do this. These are birds called chuckers. And when they run up really, really steep slopes, they use their wings to actually push them into the road surface. What that does is it lets them run more quickly up steeper slopes. This is kind of awesome. This is something that actually happens in the biological world, the living world as well. Now let's look at another problem involving vehicles on roads, okay? And I'm starting with this kind of stuff because it's fairly easy to wrap your mind around these kinds of things, but we will come back to the living world. Don't you worry. And here's the problem. What is the magnitude of the forward force required to make a Corvette go down the highway at a constant speed? And we're given some data about the car right here. Okay, so we're going to go ahead and take a look at that problem. And how do we do it? We're going to start by doing our strategy. Okay, we're going to do our strategy. How are we going to solve this problem? Well, the car is moving down the road at a constant speed. So this is a uniform motion problem, okay? Uniform motion. So we can use our relationships for uniform motion. And one of the things that's true in uniform motion is the acceleration is equal to 0. And that suggests to me that rather than thinking about acceleration, I'm going to mostly be paying attention to forces, okay? Next piece of the puzzle is we're going to do our preparation. So first we're going to start with a motion diagram. Well, the motion diagram is fairly straightforward. You have a car moving down the road at a constant speed. So my positions are the same distance apart. My velocity vectors are all the same length. That's my motion diagram. What can I say about the acceleration? The acceleration is equal to 0. Next piece of the puzzle, I'm going to draw a free body diagram. And for the free body diagram, I want to talk about what I can say about the net force. Now, a free body diagram is going to look like this. Car is moving down the road at a constant speed. What are the forces that act and in what direction? Well, the first one I always put on is a downward weight force. Then there better be something opposite that, or the car is going to accelerate downward. So there's an upward normal force. There's a forward force, okay? There's a forward force. And it turns out that's actually a static friction force. It's the friction between the tires and the road surface. That's the only possible force that we can have. And there's a backward force too, and the backward force is drag. It's drag. The car is experiencing air resistance. It's having to push air aside to go through. And the Corvette is aerodynamic, but it's still going to take it some force to kind of like move against, to push the air out of the way as it goes. So there will be a drag force. Now, what can we say about the net force? Well, since we said the acceleration was equal to 0, that lets us say something about the net force, and we can say F net is equal to 0. Now, I'm going to rewrite that free body diagram on this slide, and we're going to talk about doing our solution. I have an upward normal force. I have a downward weight force. I have a forward friction force. That's the force necessary to make the car go forward. And I got a backward drag force. I can write down an equation for the vertical and the horizontal components of the force, and it's fairly straightforward. Since F net is equal to 0, and that's true in both the x and y directions, that tells me that the normal force is equal to the weight force, and the drag force is equal to the friction force. Those are my equations. And I can solve those problems and equations, and specifically I want to look at this one. Okay, I want to look at the drag force is equal to the friction force. Now the friction force is what we're looking for. That's the force necessary to make the car go forward. But that's just equal to the drag force, and we have an expression for the drag force. It's 1/2 times the drag coefficient times the density of air times the cross-section area times the square of the speed. Now check it out. We were given the drag coefficient in the problem. We were given the density, we were given the cross-section area, and we're given the speed. We have everything we need to calculate the drag force. And so we're done. We're ready to do a computation. And when we do it, it turns out that the force necessary to make the car go down the road it's only 190 newtons. 190 newtons is not much if we want to put that in pounds to make more sense of it. That's about 40 pounds. That's about 40 pounds. 40 pounds of force. And that is not much. And so my assessment is this seems rather surprising to me. But this is one of those cases where the world is just really, really surprising. But in retrospect, maybe not so much. This is a really aerodynamic car, and I want to use very little force to make this move forward. And so that seems quite reasonable. Now, something I want you to think about is this. Milo, my dog, can pull with a force of about 40 pounds. So when I'm driving my car to the store, why don't I just take Milo and hitch him up to the front of the car? Because Milo would totally do this. Look at that can-do spirit in that chap right there. If I hitched him to the front bumper of my Scion XB, he would say, "Oh, buddy, let's do this. I am taking you down the road." But there is more to the story. And Milo can provide plenty of force, but what he can't provide is power. And so this is a question we will revisit when we talk about energy and power. But I do want to think about this. Why do you have the amazingly kind of like forceful engine underneath the hood if it only takes 190 newtons to go forward? Why do you want a big engine in your car? And now let's look at a second problem. Let's look at the force necessary to get a car up to speed. Okay, so here's my question. What is the force required to accelerate a 1,500 kilogram Corvette from rest to a top speed of 27 meters per second in 4 seconds? And we know it can probably do that because given the results of the previous problem we did. In this case, we're told you can ignore the drag force. And the drag force isn't big, okay? It was around 190 newtons, and it turns out, given the force we're going to see in this problem, we will be rather justified in doing that. How do we solve this problem? We'll solve it the way we always do. We're going to start by strategizing, okay? How will we treat this problem? Well, the car is accelerating, and we're going to assume that it's accelerating with a constant acceleration. Okay, that's what we're going to assume that. We're going to model that. And with a constant acceleration, we can use Newton's second law to basically get us to force, because fundamentally we're being asked to solve for force. So we're going to look at the motion with constant acceleration, and we're going to use that to say something about the force. Now we'll do a preparation step the way that we always do. We're going to start with a motion diagram, and our motion diagram is this. The car is speeding up, the points are getting further and further apart, the velocity vectors are getting bigger, and since that's true, there is an acceleration directed to the right. Okay, that's my motion diagram. Next piece, I can draw a free body diagram, and the free body diagram is going to look like this. Okay, there's a downward weight force, always. There's going to be an upward normal force. And there's going to be a force going to the right in the direction of the acceleration. That's going to be my static friction force, of course. Okay? Now we can write down expressions for the net force on the horizontal and vertical axes. On the vertical axis, okay, F net is just equal to the upward force minus the downward force. On the x-axis, F net is just equal to Fs. It's just equal to Fs. Now let's start our solution by doing Newton's law on the two axes. On the vertical axis, we can just say there is no acceleration vertically. That would be more, a flying car, and we don't have those yet. No matter what scientists and society has promised us, the acceleration is equal to 0. That tells me that the net force is equal to 0. If that's true, I can say the normal force is equal to the weight force. Now on the x-axis, the acceleration is not equal to 0. In fact, back when we strategized, we said we're going to use acceleration to find forces. Okay? The acceleration is something we can actually compute. We'll come back to that. But since the acceleration is not equal to 0, the acceleration is just equal to F net divided by m. Well, F net is just equal to Fs divided by m. And we're looking for a force. So Fs, the force we're looking for, is equal to m times a. And with that in hand, we're ready to continue our solution. And to do it, we're first off going to look at the magnitude of the acceleration. Okay, magnitude of the acceleration. Well, we know acceleration is just equal to delta v over delta t. And in the problem statement, we were told what delta v was. It's going from 0 to 27 meters per second. And it's doing it in a time of 4 seconds. So that gives us a value for the acceleration of 6.75 meters per second squared. And then we can just calculate Fs, the forward force on the car, is just equal to m times a. But I know the mass is 1,500 kilograms, and so I have everything in hand to calculate the force necessary to make the car go forward, and we get 10,000 newtons. 10,000 newtons. Well, that's a lot more than the 190 newtons necessary to make the car go forward at a constant speed. And so the big engine under the hood isn't to keep the car going down the road. It's to provide for rapid acceleration, so quick changes in speed. We can also see that we're justified in ignoring the drag force. And now we're going to do our assessment. 10,000 newtons is about 2,300 pounds. But this is a very, very powerful car, and so we expect it to be able to provide a lot of force. And we said previously that the drag force is like 190 newtons. And we're talking about a force of 10,000 newtons. That's a couple percent. And so within the kind of accuracy with who we're working with, it is perfectly okay to ignore the drag. And so the way we solve the problem is okay. We ended up with a very reasonable result. And if I want that kind of force, I can either get 60 Milos, which would be awesome, a team of 60 Milos pulling my car down the road, or I could get 1 Rhino. But actually, even to do that, there's more to the story, because it's not just about force, it's about power. And that is something we will talk about when we get back to talking about energy. But before we get there, we have more to do about motion and forces. And before we get there, we have our next big task, which is exam number 1, which will be on Friday, September 18th.